So what's important here is that you go back and maybe you look at this a few times and you begin to realize where these substitutions came from. If you understand the reasoning by which these substitutions take place, then you can repeat them yourself at one point. Any of these substitutions were not extensions of anything other than the formula sheet, equations that you are given. Okay, I don't want you to have a melted brain, so you might want to stop here, look back, kind of take your time to understand the first components. We're not going to talk about the last component of the CRT. The last component of the CRT occurs when the electron leaves the deflecting plates at this point, and as it leaves, it has a determined now velocity. That velocity is going to be right down this path right here. And that velocity is made up of some x velocity, which it had from the original accelerating plates, and some y velocity, which it has just attained from these vertically deflecting plates. So that's the y velocity right there. So you'll see that this velocity, this v final, is made up of a v final in the x and a v final in the y. Now from here, we are interested in determining what this deflection is right here. Right here we have this deflection in the y, which we can call dys, which stands for deflection in the y on the screen. So you can see here that you have a big triangle. You've got a distance from when it leaves the plates to when it hits this screen up here. That is my x to the screen. I have a deflection in the y on the screen, and I have this big triangle which has an angle in it defined by the angle created by the final y velocity, the final x velocity. So now that we have this understanding here on the paper, let me transfer that drawing. Okay, so we have the accelerating plates, the deflecting plates. Inside of the deflecting plates, we have this bit of deflection right here. That there is the dyp that we've just been talking about for the last little while. And outside of the plates, we have a deflection which is measured from right here. From there to there is my deflection in the y on the screen. I have my distance from here to the screen as my dx to the screen. And I can see the parabolic motion here and then a straight line to the screen. That straight line is transversed by the particle, in this case an electron, and it has its velocity directed down that same path. So what we end up getting in here is a case of similar triangles. These are those similar triangles. We have a velocity triangle, which is the v final on the hypotenuse. We've got our v final in the y and our v final in the x, which so happens to be the v final a of the previous diagram that we had, because this value is not changing throughout the system. The velocity that the electron has after leaving the accelerating plates maintains all the way through. And the difference becomes then just the fact that we've accelerated the electron in this direction between these two plates. So now it has some y velocity as well. And those two add together as vectors do to create a final velocity, which is the combination of the two. The mathematics connected with that, recall, is that Vf equals Vfx squared plus Vfy squared, because these two are perpendicular to each other. Now the second triangle we have is the distance triangle, where we have dys here, we have dxs there, and we have an angle in here, theta. This angle theta is the same as that angle there. So we could recall from our earlier kinematics that that angle, theta, is equal to the arctangent of Vfy over Vfx. So now I know the angle here. So if I'm given the distance, this distance, I should be able to find that distance, because I have a similar relationship over here that theta, or I'll back it up a little bit more, the tangent of theta equals dys over dxs. So here's another component of the CRT where the mathematics involved is different than the other two. We had a conservation of energy to begin with. We then had a kinematics and force dynamics situation. And lastly, we have similar triangles to indicate to us whatever values we want to find here are solved using similar triangles and earlier kinematics.